Reading Practice, PhD Civil and Environmental Engineering Guideline prepared by Hammad Al-Khayari, Chapter 1, Introduction to Civil and Environmental Engineering 1.1 Overview of Civil Engineering. Civil engineering is one of the oldest and most essential branches of engineering, dedicated to the planning, design, construction, and maintenance of the physical and naturally built environment. This includes infrastructure such as roads, bridges, dams, buildings, and airports. Civil engineers apply principles from various fields, including physics, mathematics, and materials science, to ensure the safety, sustainability, and functionality of these structures. The discipline is subdivided into various specialties, including structural, geotechnical, transportation, water resources, and construction engineering. 1.2 Importance of environmental engineering. Environmental engineering is a critical subset of civil engineering that focuses on protecting human health and the environment by improving waste disposal methods, minimizing pollution, and managing natural resources sustainably. As global awareness of environmental issues rises, the role of environmental engineers becomes increasingly vital. They work on projects related to water and air quality, waste management, and remediation of contaminated sites, helping to develop technologies and strategies that mitigate environmental impacts and promote sustainability. The integration of environmental considerations into civil engineering practices is essential for fostering a healthier planet. 1.3 Interdisciplinary nature of the field. Civil and environmental engineering is inherently interdisciplinary, integrating knowledge from diverse fields such as geology, hydrology, chemistry, biology, and urban planning. This interdisciplinary approach enables engineers to tackle complex problems that arise in the design and management of infrastructure and environmental systems. Collaboration with scientists, policymakers, and communities is essential to develop comprehensive solutions that consider technical feasibility, economic viability, and social impact. By bridging various disciplines, civil and environmental engineers can innovate and implement sustainable practices that address the challenges of modern society. 1.4 Scope and applications. The scope of civil and environmental engineering is vast, encompassing a wide range of applications that address both current and future challenges. Key areas include infrastructure development, designing and constructing roads, bridges, and buildings that meet the growing demands of urbanization and population growth. Water resource management, ensuring the availability and quality of water through effective water supply systems, wastewater treatment, and flood control measures. Sustainable design, implementing green building practices and renewable energy systems to reduce the environmental impact of construction and operation. Transportation systems, developing efficient and sustainable transportation networks that enhance mobility while minimizing congestion and pollution. Environmental remediation, designing strategies for cleaning up contaminated sites and restoring ecosystems affected by industrial activities. By addressing these diverse areas, civil and environmental engineers play a crucial role in shaping a sustainable future, improving the quality of life, and safeguarding the environment for generations to come. Chapter 2, Public Sector Roles of Civil and Environmental Engineers. 2.1 Governmental Agencies and Authorities. 2.1.1 Federal Agencies. 2 Civil and environmental engineers often work with various federal agencies that play crucial roles in infrastructure development and environmental protection. Agencies such as the Federal Highway Administration, FHWA, the Environmental Protection Agency, EPA, and the Army Corps of Engineers are key players. These agencies are responsible for establishing regulations, providing funding, and overseeing projects that ensure public safety and environmental sustainability. Engineers collaborate with these agencies to develop policies, conduct research, and implement national standards that guide civil engineering practices across the country. 2.1.2 State and local authorities. At the state and local levels, civil and environmental engineers engage with authorities responsible for public infrastructure within their jurisdictions. State departments of transportation, DOTs, and local public works departments are integral to planning, designing, and maintaining roads, bridges, water supply systems, and waste management facilities. Engineers in this realm must navigate local regulations, engage with communities, and ensure that projects meet both state and federal guidelines. Their roles often extend to project management, stakeholder communication, and public outreach to foster transparency and community involvement. 2.2 Responsibilities in Public Works. 2.2.1 Planning and Design. The planning and design phase is critical for civil and environmental engineers involved in public works. This phase encompasses feasibility studies, environmental impact assessments, and the development of detailed designs that align with regulatory requirements. Engineers must consider factors such as safety, sustainability, and community needs while creating plans that fit within budgetary constraints. Collaboration with urban planners, architects, and environmental scientists is essential to produce comprehensive and effective designs for infrastructure projects. 2.2.2 Construction Oversight. During the construction phase, civil and environmental engineers are tasked with oversight to ensure that projects are built according to design specifications and regulatory standards. This involves regular site inspections, coordination with contractors, and troubleshooting any issues that arise during construction. Engineers must enforce safety protocols and quality control measures while adhering to timelines and budgets. Effective communication and problem-solving skills are vital as they work to resolve conflicts between various stakeholders involved in the project. 2.2.3 Maintenance and Management. Once construction is complete, civil and environmental engineers play a key role in the ongoing maintenance and management of public infrastructure. This includes developing maintenance plans, conducting regular inspections, and implementing necessary repairs or upgrades. Engineers must also assess the condition of existing structures and systems to ensure they continue to meet safety and performance standards over time. Their work in this area is vital for extending the lifespan of infrastructure and ensuring that public resources are used efficiently. 2.3 Regulation of Private Civil Engineering Works. 2.3.1 Design Codes and Standards. Civil and environmental engineers are responsible for adhering to and enforcing design codes and standards that govern private engineering works. These codes ensure that constructions are safe, functional, and environmentally responsible. Engineers must stay updated on local, state, and federal regulations, and they often participate in the development of these standards. This includes guidelines for materials, structural integrity, environmental impact, and sustainability practices. Compliance with these codes is critical for obtaining necessary permits and approvals for private projects. 2.3.2 Compliance and Enforcement. Compliance and enforcement of engineering standards are essential to protect public health, safety, and welfare. Civil and environmental engineers often work alongside regulatory agencies to ensure that private projects conform to established codes and standards. This involves reviewing plans, conducting site inspections, and assessing compliance with environmental regulations. Engineers may also be involved in responding to violations and implementing corrective actions when necessary. Their role in this enforcement process helps to maintain the integrity of the engineering profession and ensures that private developments contribute positively to the community and environment. Chapter 3, Key Infrastructure and Engineering Works. Infrastructure plays a critical role in the development and functioning of modern societies. This chapter outlines the essential components of infrastructure and engineering works, categorizing them into building structures, for transportation infrastructure, public transportation systems, energy infrastructure, and water and waste management systems. 3.1 Building structures. Building structures form the backbone of urban and rural environments, housing residential, commercial, and institutional functions. Their design and construction must consider safety, sustainability, and resilience to natural disasters. Key aspects include design principles, emphasis on aesthetics, functionality, and user experience. Materials and techniques, utilization of advanced materials, example steel, concrete, glass, and construction techniques, example prefabrication, modular construction. Sustainability, incorporating energy-efficient designs, green roofs, and sustainable materials to minimize environmental impact. 3.2 Transportation infrastructure. Transportation infrastructure is vital for facilitating the movement of people and goods. It encompasses various components, each playing a distinctive role in the overall connectivity of regions. 3.2.1 Roads and highways. Roads and highways are crucial for land transportation, connecting cities and towns. They vary in design and capacity, from local streets to major interstate highways. Key considerations include road design, geometric design principles, traffic flow management, and safety measures. Maintenance, regular upkeep to ensure safety and efficiency, including resurfacing, pothole repairs, and upgrades. 3.2.2 Bridges and tunnels. Bridges and tunnels overcome physical barriers and enhance connectivity. Their design must address engineering challenges, environmental impacts, and safety standards. 5. Bridge types, different styles, example beam, arch, suspension, based on span requirements and aesthetic considerations. Tunnel engineering, techniques for construction, example cut and cover, boring, and ventilation systems for safety. 3.2.3 Airports and ports. Airports and ports are critical for international trade and travel. They serve as gateways for goods and passengers, necessitating advanced infrastructure and operational efficiency. Airport infrastructure, runways, terminals, and air traffic control systems designed for safety and capacity. Port facilities, docks, cargo handling systems, and navigation aids to support maritime trade. 3.3 Public transportation systems. Public transportation systems provide affordable and efficient mobility options for urban populations. They reduce congestion, lower emissions, and enhance accessibility. Key components include bus rapid transit, BRT dedicated lanes for buses to improve travel times and reliability. Subways and light rail, electrified rail systems that offer rapid urban transit solutions. Integrated ticketing systems, seamless fare collection across different modes of transport. 3.4 Energy infrastructure. Energy infrastructure is essential for powering homes, businesses, and industries. It includes a mix of traditional and renewable sources to ensure a reliable energy supply. 3.4.1 Power plants. Power plants convert various energy sources, example fossil fuels, nuclear, hydroelectric, into electricity. Key considerations include 6. Types of power generation, understanding the operational dynamics of thermal, hydro, and renewable power plants. Environmental impact, implementing technologies to reduce emissions and comply with regulations. 3.4.2 Renewable energy sources. The integration of renewable energy sources is crucial for sustainable development. This includes solar, wind, geothermal, and biomass energy. Solar farms, large-scale solar installations and distributed photovoltaic, PV, systems. Wind turbines, onshore and offshore wind farms contributing to grid energy. 3.5 Water and waste management systems. Water and waste management systems are vital for public health and environmental sustainability. They ensure the availability of clean water and the proper treatment of waste. 3.5.1 Water supply systems. Water supply systems involve the sourcing, treatment, and distribution of potable water. Key aspects include water treatment plants, processes for purifying water to meet health standards. Distribution networks, pipeline infrastructure delivering water to homes and businesses. 3.5.2 Wastewater treatment facilities. Wastewater treatment facilities are designed to treat sewage and industrial waste before it is released into the environment. Treatment processes, primary, secondary, and tertiary treatment stages to remove contaminants. Reclamation, technologies for recycling treated water for non-potable uses. 3.5.3 Solid waste management. Effective solid waste management systems are essential for maintaining public health and environmental integrity. Collection and transportation, systems for efficiently collecting and transporting waste. Disposal and recycling, landfills, incineration, and recycling programs aimed at reducing waste and promoting sustainability. This chapter outlines the fundamental components of infrastructure and engineering works essential for the functioning and development of modern societies. Each section emphasizes the importance of design, sustainability, and innovation in meeting the challenges of the future. Chapter 4, Collaborative Practices in Civil Engineering. Collaboration is a cornerstone of successful civil engineering projects. It involves not only teamwork among engineers but also partnerships with architects, contractors, and other stakeholders. This chapter explores various collaborative practices essential for civil engineering, emphasizing the importance of effective communication, mutual respect, and shared goals. 4.1 Working with other engineers. Collaboration among engineers is critical in any civil engineering project. Engineers from different disciplines such as structural, geotechnical, environmental, and transportation must work together to ensure the project's success. Here are some key aspects of effective collaboration among engineers. 8. Interdisciplinary communication. Regular meetings and updates are vital for maintaining clear communication. Engineers should utilize collaborative tools such as project management software and shared documents to keep everyone informed and engaged. Defining roles and responsibilities. Clearly defining each engineer's role helps avoid overlap and confusion. This clarity ensures that all aspects of the project are covered and that team members can focus on their specific tasks. Problem solving. Together, engineers should adopt a collaborative approach to problem solving. When challenges arise, brainstorming sessions can lead to innovative solutions that might not be evident when working in silos. Continuing education and training. Engaging in joint training sessions and workshops can enhance team cohesion and ensure that all engineers are up to date with the latest technologies and practices in their respective fields. 4.2 Collaboration with architects. Collaboration between civil engineers and architects is crucial for the successful design and execution of projects. The interplay between structural integrity and aesthetic design requires ongoing dialogue and coordination. The following points highlight effective collaboration. Early involvement. Civil engineers should be involved in the early stages of the design process. This early collaboration ensures that structural considerations are integrated into the architectural vision from the outset. Shared design tools. Utilizing building information modeling, BIM, allows both architects and engineers to visualize the project comprehensively. This shared platform facilitates real-time updates and adjustments, minimizing misunderstandings. Feedback loops. Establishing a feedback mechanism where architects can provide input on structural designs and engineers can advise on design feasibility fosters a productive working relationship. 9. Joint site visits. Conducting site visits together allows both parties to understand the practical implications of design decisions and identify potential challenges before they arise. 4.3 On-site inspections and fieldwork. On-site inspections and fieldwork represent the practical aspect of civil engineering and are crucial for successful project execution. Collaboration during these phases is essential for ensuring that designs are implemented correctly and that any arising issues are addressed promptly. Team coordination. During site inspections, engineers, architects, and contractors should work as a unified team. Regular coordination meetings on site can help ensure that everyone is aligned with the project goals and timelines. Documentation and reporting. Thorough documentation of site conditions and inspection results is vital. Engineers should collaborate with other team members to maintain accurate records that can inform future decisions. Safety protocols. Collaboration extends to ensuring that safety protocols are adhered to on-site. All team members must be aware of safety regulations and practices to protect themselves and others. Adaptive problem solving. Fieldwork often presents unexpected challenges. A collaborative approach to problem solving on-site, where team members can brainstorm solutions together, leads to quicker and more effective resolutions. In conclusion, collaborative practices in civil engineering are essential for fostering innovation, ensuring project success, and enhancing team dynamics. By promoting open communication, mutual respect, and an interdisciplinary approach, civil engineers can work effectively with their peers and other stakeholders to deliver high-quality infrastructure that meets societal needs. Chapter 5, Laboratory Practices in Civil Engineering. 10 Laboratory practices play a crucial role in civil engineering, providing essential insights and data necessary for the design, construction, and maintenance of infrastructure. This chapter outlines the fundamental laboratory practices associated with various subdisciplines within civil engineering, detailing the specific materials and methods employed in each area. 5.1 Asphalt and Bituminous Material Labs. Asphalt and bituminous materials are vital for road construction and maintenance. Laboratories specializing in these materials focus on testing properties, evaluating the physical and chemical properties of asphalt, including penetration, softening point, and viscosity. Mix design, developing optimal asphalt mixtures through methods such as the Marshall and Superpave designs, ensuring durability and performance. Performance evaluation, conducting tests like the Hamburg wheel tracking test and the asphalt pavement analyzer to assess resistance to deformation and moisture susceptibility. Field sampling and quality control, implementing protocols for sampling asphalt mixtures and monitoring quality during production and application. 5.2 Concrete material testing. Concrete is a primary construction material, and its performance is influenced by various factors. Concrete material testing labs perform material characterization, analyzing the properties of constituent materials, cement, aggregates, water, and admixtures, to ensure quality. Strength testing, conducting compressive, tensile, and flexural strength tests on concrete specimens to verify compliance with design specifications. 11. Durability assessment, evaluating the resistance of concrete to environmental factors, including freeze-thaw cycles, sulfate attack, and chloride ingress. Workability tests, measuring the workability of fresh concrete using methods such as the slump test, flow table test, and web test. 5.3 Environmental engineering labs. Environmental engineering labs focus on protecting human health and the environment through the study of various pollutants and waste management techniques. Key activities include water quality testing, analyzing water samples for contaminants, including heavy metals, nutrients, and pathogens, using techniques like spectrophotometry and chromatography. Soil and groundwater analysis, assessing soil and groundwater for pollutants, employing techniques such as soil leaching tests and groundwater sampling. Waste management studies, evaluating the characteristics of solid and hazardous wastes and determining appropriate treatment and disposal methods. Air quality monitoring, measuring air pollutants and assessing compliance with environmental regulations. 5.4 Geotechnical and Soil Mechanics Labs. Geotechnical engineering labs investigate soil properties to inform foundation design and earthwork projects. Key functions include soil classification, performing tests such as the Atterberg limits, sieve analysis, and hydrometer tests to classify soil types. Shear strength testing, conducting triaxial, unconfined compression, and direct shear tests to determine soil shear strength parameters. Consolidation testing, assessing soil compressibility through odometer tests to predict settlement behavior under loads. 12. Permeability testing, measuring the hydraulic conductivity of soils using falling head and constant head permeability tests. 5.5 Hydrology and Hydraulics Labs. Labs specializing in hydrology and hydraulics focus on the behavior of water in the environment and its interactions with structures. Activities include flow measurement, utilizing flumes, weirs, and flow meters to measure surface water flow rates in various conditions. Hydraulic modeling, constructing physical and computational models to study flow behavior around structures, including dams and bridges. Rainfall runoff studies, analyzing watershed responses to rainfall events using simulation models and empirical methods. Sediment transport analysis, investigating sediment movement in water bodies and its implications for erosion and deposition processes. 5.6 Structural Computing and Testing Labs. Structural computing and testing labs focus on analyzing and testing the performance of structures under various loads. Key practices include, finite element analysis, via using computational software to model and analyze structural behavior under static and dynamic loads. Load testing, conducting full-scale load tests on structural elements such as beams, columns, and bridges to verify design assumptions. Material testing, evaluating the mechanical properties of construction materials, such as steel and composites, under various loading conditions. 13. Non-destructive testing, NDT, implementing techniques like ultrasonic testing and radiography to assess the integrity of structures without causing damage. 5.7 Transportation and GIS labs. Transportation and GIS, Geographic Information Systems, labs focus on infrastructure planning, traffic analysis, and spatial data management. Key functions include, traffic flow analysis, monitoring and analyzing traffic patterns using video surveillance and sensors to improve roadway efficiency. GIS mapping, utilizing GIS software to create and analyze spatial data for transportation planning and infrastructure development. Transportation modeling, developing models to predict traffic behavior and assess the impact of transportation projects on existing systems. Surveying and remote sensing, employing surveying techniques and remote sensing technology to collect data for transportation infrastructure design and maintenance. This chapter underscores the importance of laboratory practices in civil engineering, highlighting the necessity of rigorous testing, analysis, and modeling to ensure the safety, sustainability, and efficiency of infrastructure projects. Chapter 6, the PhD Program Structure. 6.1 Program Overview. The PhD program in Civil and Environmental Engineering is designed to equip students with advanced knowledge and research capabilities in various specialized areas. The program emphasizes both theoretical understanding and practical application, fostering skills necessary for innovative research and problem-solving in real-world contexts. 14 students will engage in rigorous coursework, hands-on learning, and independent research to prepare for careers in academia, industry, or government. 6.2 Core Civil and Environmental Engineering Streams. The program features several core streams that represent key areas of study within civil and environmental engineering. Each stream offers focused coursework and research opportunities, enabling students to develop expertise in their chosen field. 6.2.1 Structures and Geotechnics. The stream focuses on the design, analysis, and performance of structures, including buildings, bridges, and other infrastructure. It covers topics such as structural mechanics, materials science, and geotechnical engineering. Students will engage in research on the behavior of structures under various loads, soil structure interaction, and innovative materials and construction techniques. 6.2.2 Hydraulics and Water Resources. The Hydraulics and Water Resources stream addresses the management and engineering of water resources, including surface water and groundwater systems. Key topics include fluid mechanics, hydrology, hydraulic engineering, and water quality management. Students will conduct research on water distribution systems, flood management, and sustainable practices for water resource allocation. 6.2.3 Transportation Engineering. This stream examines the planning, design, and operation of transportation systems. Topics include traffic flow theory, transportation planning, and the environmental impacts of transportation. Students will explore innovative solutions for improving mobility and sustainability in urban and rural contexts, conducting research on smart transportation systems and policy implications. 6.2.4 Environmental Sustainability. Focusing on sustainable practices in civil and environmental engineering, this stream emphasizes the integration of ecological principles into engineering design and decision-making. Key areas of study include waste management, 15 renewable energy systems, and sustainable infrastructure. Students will engage in research that promotes environmental stewardship and addresses climate change challenges. 6.3 Research Methodologies. The PhD program emphasizes diverse research methodologies essential for conducting rigorous scientific investigations. Students will be trained in both qualitative and quantitative research approaches, including experimental design, statistical analysis, modeling and simulation, and field studies. This training will prepare students to formulate research questions, design studies, and analyze data effectively. 6.4 Coursework and hands-on learning. Coursework in the PhD program is a blend of foundational and specialized subjects, designed to enhance theoretical understanding and practical skills. Students will participate in workshops, seminars, and collaborative projects that promote experiential learning. Hands-on learning opportunities may include laboratory work, field studies, and internships with industry partners, providing real-world context to academic knowledge and fostering professional development. Through this structured program, students will emerge as competent researchers and practitioners, ready to contribute meaningfully to the field of civil and environmental engineering. Chapter 7: Sustainable Engineering Practices. In an era where environmental concerns significantly influence engineering practices, sustainable engineering has emerged as a key discipline. This chapter delves into the principles of sustainable design, the importance of environmental impact assessments, and effective climate change mitigation strategies. 7.1 Principles of Sustainable Design. 16 Sustainable design is an approach that seeks to minimize negative environmental impacts while enhancing the quality of life for current and future generations. The following principles are essential to sustainable design. 1. Resource efficiency. Optimize the use of materials, energy, and water throughout the life cycle of a product or structure. This includes selecting sustainable materials, reducing waste, and enhancing energy efficiency. 2. Life cycle thinking. Evaluate the environmental impacts of a product from cradle to grave. This involves assessing every stage: extraction, manufacturing, use, and disposal, with the aim of reducing the overall footprint. 3. Ecosystem integration. Design should harmonize with natural ecosystems, preserving biodiversity and promoting ecological health. This includes utilizing natural processes and materials, as well as respecting the local environment. 4. Social responsibility. Sustainable design must also consider social equity and community well-being. This involves engaging stakeholders, promoting inclusivity, and ensuring that designs benefit all members of society. 5. Adaptability and resilience. Structures and systems should be designed to adapt to changing conditions and withstand environmental stressors, including climate change impacts. 6. Simplicity and modularity. Emphasize simplicity in design to reduce complexity and enhance maintenance. Modular components can facilitate repairs, upgrades, and recycling. 7.2 Environmental impact assessments. Environmental impact assessments, EIAs, are critical tools for evaluating the potential environmental effects of proposed projects before they are carried out. The EIA process consists of several key steps. 1. Screening. Determine whether a project requires an EIA based on its potential to significantly affect the environment. 17.2. Scoping. Identify the key issues and impacts to be assessed, involving stakeholders to ensure that all concerns are addressed. 3. Impact analysis. Conduct a detailed analysis of potential environmental impacts, including direct, indirect, and cumulative effects. This may involve quantitative assessments, modeling, and expert consultations. 4. Mitigation measures. Develop strategies to avoid, minimize, or compensate for identified impacts. This may include redesigning a project, employing new technologies, or implementing conservation practices. 5. Reporting. Compile findings into an EIA report that summarizes the assessment results, proposed mitigation measures, and recommendations for decision makers. 6. Decision making. The relevant authorities review the EIA report to make informed decisions regarding project approval, considering both environmental and socio-economic factors. 7. Monitoring and compliance. Establish a framework for ongoing monitoring of environmental impacts during project implementation and ensure compliance with regulatory requirements. 7.3 Climate change mitigation strategies. Addressing climate change requires a multifaceted approach that includes various mitigation strategies. Engineers play a crucial role in implementing these strategies, which include: 1. Renewable energy integration, transitioning from fossil fuels to renewable energy sources such as solar, wind, and geothermal to reduce greenhouse gas emissions. 2. Energy efficiency improvements, enhancing the energy efficiency of buildings, transportation systems, and industrial processes through better design, technology, and practices. 18.3. Carbon capture and storage, CCS, developing technologies to capture carbon dioxide emissions from industrial processes and store them underground to prevent them from entering the atmosphere. 4. Sustainable transportation, promoting public transportation, electric vehicles, and non-motorized transportation options to reduce emissions from the transportation sector. 5. Urban planning and green infrastructure, designing cities and communities to be more sustainable through green spaces, efficient public transport systems, and environmentally friendly building practices. 6. Waste reduction and recycling, implementing strategies to minimize waste generation and promote recycling and upcycling to reduce landfill contributions and resource extraction. 7. Climate resilient infrastructure, designing infrastructure that can withstand the impacts of climate change, including extreme weather events, sea level rise, and temperature fluctuations. By integrating these sustainable engineering practices, we can work towards a more sustainable future that addresses environmental challenges and promotes economic and social well-being. Chapter 8, Challenges in Civil and Environmental Engineering. 8.1 Emerging Issues in Infrastructure. The infrastructure sector faces numerous emerging issues that threaten the sustainability and functionality of essential services. Key challenges include, aging infrastructure. Many cities are grappling with deteriorating roads, bridges, and water systems that require urgent repair or replacement. The financial burden of upgrading these systems is substantial, necessitating innovative funding solutions. 19. Sustainability goals. As environmental concerns grow, infrastructure development must align with sustainability principles. This includes the use of eco-friendly materials, energy-efficient designs, and practices that minimize environmental footprints. Resilience to disruptions. Infrastructure systems must be designed to withstand not only natural disasters but also human-made disruptions, such as cyber attacks. This resilience requires integrated planning and investment in advanced technologies. Funding and investment. Securing adequate funding for infrastructure projects is a persistent challenge. Public-private partnerships and innovative financing models may offer potential solutions to bridge funding gaps. 8.2 Climate change and natural disasters. Climate change poses unprecedented challenges to civil and environmental engineering, impacting both the design and maintenance of infrastructure. Key considerations include, increased frequency of extreme weather events. Engineers must account for more frequent and severe storms, floods, and heat waves in their designs. This necessitates the use of adaptive design principles and materials that can withstand these conditions. Rising sea levels. Coastal infrastructure is particularly vulnerable to rising sea levels. Engineers need to develop strategies for protecting coastal cities, such as sea walls, levees, and marsh restoration. Water resource management. Changes in precipitation patterns and increased evaporation rates challenge traditional water management systems. Innovative approaches to water conservation, stormwater management, and wastewater recycling are essential. 20. Environmental impact assessments. Comprehensive assessments that account for climate change impacts must become standard practice in project planning. This includes evaluating potential risks and developing mitigation strategies. 8.3 Urbanization and population growth. Rapid urbanization and population growth present significant challenges and opportunities for civil and environmental engineering. Infrastructure demand. As cities expand, the demand for housing, transportation, and utilities increases. Engineers must find efficient ways to meet these demands without compromising quality or sustainability. Smart cities. The integration of technology in urban planning can lead to the development of smart cities that optimize resource use and enhance the quality of life for residents. This includes intelligent transportation systems, energy-efficient buildings, and data-driven decision-making. Social equity. Urbanization often exacerbates social inequalities, as marginalized communities may lack access to quality infrastructure. Engineers must advocate for inclusive planning that addresses the needs of all citizens. Green spaces. The preservation and creation of green spaces in urban areas can improve air quality, reduce heat islands, and enhance residents' well-being. Incorporating green infrastructure into urban planning is crucial. 8.4 Technological advancements. Technological innovations are transforming the field of civil and environmental engineering, offering new tools and methodologies to address existing challenges. 21. Building information modeling. BIM technology enhances collaboration, visualization, and efficiency in project planning and execution. It allows for better resource allocation and life cycle management of infrastructure. Renewable energy integration. The shift towards renewable energy sources requires engineers to design infrastructure that accommodates solar, wind, and other sustainable technologies. This includes energy-efficient buildings and smart grids. Data analytics and AI. The use of data analytics and artificial intelligence in infrastructure management can improve decision-making processes, predictive maintenance, and resource allocation. Sustainable materials. Advances in materials science are leading to the development of sustainable construction materials that reduce environmental impacts. This includes recycled materials and innovations like self-healing concrete. Drones and robotics. Drones and robotic technologies are revolutionizing surveying, inspection, and maintenance processes, allowing for safer and more efficient operations. In conclusion, civil and environmental engineering faces a multitude of challenges that require innovative solutions and proactive strategies. By addressing these emerging issues, engineers can contribute to creating resilient, sustainable, and equitable infrastructure for future generations. Chapter 9. Career Opportunities and Professional Development. In this chapter, we will explore various career pathways available across different sectors, along with professional development strategies to enhance skills and advance in your chosen field. 9.1 Thriving Private Sector Roles. 22 The private sector offers a diverse array of career opportunities across industries such as technology, finance, healthcare, and manufacturing. Key roles include: business analyst, focuses on analyzing data and processes to support business decisions. Project manager, oversees projects from inception to completion, ensuring they meet deadlines and budgets. Marketing specialist, develops and implements marketing strategies to attract and retain customers. Software developer, designs, codes, and maintains software applications, with roles varying from front-end to back-end development. Skills required: strong analytical and problem-solving abilities, excellent communication and interpersonal skills, technical proficiency relevant to the role, example programming languages for developers, adaptability to fast-paced environments. Growth opportunities. Private sector roles often provide career advancement through performance-based promotions, professional development programs, and the opportunity to switch between departments or roles within the organization. 9.2 Public sector employment. Public sector jobs are typically offered by government agencies at the local, state, and federal levels. These roles can range from administrative positions to specialized roles in public health, education, and law enforcement. Common roles: urban planner, develops plans for land use and community development. Public health administrator, oversees health programs and policies to improve community health. 23. Policy analyst, researches and analyzes public policies, advising government officials on best practices. Education administrator, manages educational institutions and programs, focusing on policy implementation and improvement. Skills required: knowledge of public administration and government processes, strong research and analytical skills, effective communication and public speaking abilities, understanding of community needs and public service ethics. Benefits of public sector employment. Public sector jobs often come with job stability, comprehensive benefits, retirement plans, and opportunities to make a significant impact on society. 9.3 Academic and research opportunities. A career in academia or research can be fulfilling for those inclined toward teaching, scholarship, and innovation. Opportunities exist at universities, research institutions, and think tanks. Roles in academia: professor, teaches courses, conducts research, and publishes scholarly articles. Research scientist, conducts experiments and investigations in various fields, contributing to knowledge and innovation. Graduate advisor, mentors and guides students through their academic programs and research projects. Skills required: 24, expertise in a specific subject area, strong research and writing skills, ability to engage and inspire students, collaborative skills for working with other researchers and faculty. Pathways to advancement: academic careers often require advanced degrees, example PhD, and can lead to positions such as department chair, dean, or director of research. 9.4 Professional certifications and licensure. Regardless of the sector, obtaining professional certifications and licenses can enhance your qualifications and demonstrate expertise. Popular certifications: Project Management Professional, PMP, validates project management skills and knowledge. Certified Public Accountant, CPA, recognizes expertise in accounting and finance. Certified Information Systems Security Professional, CISP, acknowledges proficiency in information security. Teaching licensure, required for educators to teach in public schools. Importance of certifications: certifications often lead to increased job opportunities, higher salaries, and career advancement. They serve as a testament to your commitment to professional development and mastery of industry standards. Continuous learning: engaging in lifelong learning through workshops, online courses, and professional associations can keep your skills sharp and relevant in a continually changing job market. 25 This chapter highlights the myriad career options available across sectors and emphasizes the importance of professional development in achieving long-term career success. Whether you choose to pursue opportunities in the private or public sector, academia, or through certifications, investing in your career growth will enhance your prospects and job satisfaction. Chapter 10, Conclusion and Future Directions. This chapter synthesizes the insights gained throughout the program and highlights future avenues for research and practice in civil and environmental engineering. The focus is on the integration of emerging technologies, sustainable practices, and collaborative efforts to address the challenges facing infrastructure and the environment. 10.1 Trends in Civil and Environmental Engineering. As we look to the future, several key trends are shaping the landscape of civil and environmental engineering. These include digital transformation, the integration of digital tools such as building information modeling, BIM, geographic information systems, GIS, and artificial intelligence, AI, is revolutionizing project design, management, and execution. Resilience engineering: as climate change continues to impact infrastructure, there is a growing emphasis on designing resilient systems that can withstand extreme weather events and adapt to changing conditions. Sustainable practices: an increasing focus on sustainability is driving the adoption of eco-friendly materials, energy-efficient designs, and waste reduction strategies in construction and infrastructure development. 26. Interdisciplinary collaboration: addressing complex environmental issues requires collaboration across disciplines, including urban planning, environmental science, and public policy, fostering innovative solutions that integrate diverse perspectives. 10.2 The future of sustainable infrastructure: the future of infrastructure must prioritize sustainability to meet the needs of growing populations while minimizing environmental impact. Key considerations include green building standards, the adoption of certification programs such as LEED, Leadership in Energy and Environmental Design, and BREEAM, Building Research Establishment. Environmental assessment method will continue to influence building practices, promoting energy efficiency and sustainable resource use. Circular economy, emphasizing the reuse of materials and waste reduction. The circular economy model seeks to create a closed-loop system that minimizes resource consumption and environmental degradation. Smart infrastructure, the integration of smart technologies into infrastructure, such as sensors and IoT devices, will enhance monitoring, maintenance, and operational efficiency, leading to more responsive and adaptive systems. Community engagement. Future projects will increasingly prioritize stakeholder engagement and community input in the planning and design phases, ensuring that infrastructure meets the needs of local populations and enhances quality of life. 10.3 Final thoughts on advancing the field. Advancing the field of civil and environmental engineering requires a commitment to lifelong learning, innovation, and ethical practice. As emerging challenges arise, engineers must be prepared to adapt and respond with creativity and resilience. Collaboration across disciplines, engagement with communities, and a dedication to sustainability will be essential in shaping a future where infrastructure serves both people and the planet. 27 Investing in education, research, and professional development will empower the next generation of engineers to lead the way in creating sustainable, resilient, and inclusive infrastructure systems. By embracing these principles, the civil and environmental engineering community can significantly contribute to a more sustainable and equitable future. Appendices: A list of relevant standards and codes, American Society for Testing and Materials, ASTM, Standards, International Organization for Standardization, ISO, Standards, American Institute of Steel Construction, AISC, Codes, National Fire Protection Association, NFPA, Codes. B. Key organizations in civil engineering: American Society of Civil Engineers, ASCE, National Society of Professional Engineers, NSPE, American Council of Engineering Companies, ACEC, International Federation of Consulting Engineers, FIDIC. See suggested reading and resources: Sustainable Infrastructure, Principles into Practice by Thomas Aham Vandermeer, The Civil Engineering Handbook edited by W. F. Chen and J. Y. Richard Liu, Building a Sustainable Future, The Role of Civil Engineering by David A. Hencher. 28D Glossary of Terms, BIM, Building Information Modeling, GIS, Geographic Information Systems, LEAD, Leadership in Energy and Environmental Design. Circular Economy, an economic system aimed at eliminating waste and the continual use of resources. This structure encapsulates the critical themes and discussions presented throughout the PhD program, providing a roadmap for future research, practice, and collaboration in civil and environmental engineering. 29.